Hey everybody, welcome to CS161. By now, I'm hoping that you've had a chance to browse the discussion area and you found the video that I made before the holidays on installing and using Visual Studio for the first time. If you haven't, I suggest you get on that one as well. What I wanted to do today is kind of talk about a few of the CS160 principles that we'll continue to use in CS161. 161 is definitely more of a programming class than 160. 160's objective was to teach you about different concepts in computer science with a little bit of programming. But here we're going to go deeper and start to prepare you for those more advanced classes. There's a couple things that are kind of fundamentals, right? And if you use a math analogy, right, you get into calculus and differential equations and things like that. There's certain math fundamentals that you just have to practice and practice and practice around algebra. It's kind of the same thing in this case. The first one is around base 2 or binary, right? And I'll make these slides available, of course, right? But a few things on terminology and kind of notation. We use the term bit. Bit is just a shorthand for binary digit. And in base 2, there's only 2 values for a bit, 0 and 1. In base 10, there's 10 different values. And so if I have just one character in base 10, just one digit, I can count 10 different values. But with base 2, I can only count 2. And so how does counting work in that case? You start with 0, then you go to 1, and then you're out of characters. So you got to add another digit, right? And maybe I should kind of justify these a little bit here so that looks more like that. And you can see kind of the pattern here. One thing that's very evident is that by the time I even get to the value 4, I already have 3 digits. And if I get to the value 8, I have 4 different bits. And so it's an easy question to ask is, how is this efficient? And it's less of a matter of efficiency, really. It's more of how computers are structured and how computers take advantage of this notation. And we'll talk more about this here in this session here. So let's go through an example of converting from binary to base 10. Here's an example, 10101. The way that I do it is I start from the right and I go left. There's several different ways to do it. And there's a really clever one where you go from the left to the right. But the way that I'm going to show you is you start from the left, and each bit has a positional value, a multiplier. So just like in base 10, you have your ones, your tens, your hundreds, your thousands, and so on. In binary, you have your ones, your twos, your fours, your eights, your 16s. Each digit you multiply by 2, just like in base 10, each digit you multiply by 10. And so here's the math notation, right? 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. Remember that anything to the power 0 is equal to 1. And so if I want to convert this, I basically multiply, I do these numbers here, right? And so for example, this is 16, and that's 8, that's 4, that's 2, and that's 1. I basically add up these numbers in parentheses when there's a 1 in the bit value, right? And so I get 1 plus, going from the right again, 1 plus 4 plus 16 is equal to 21. Okay, so this is standard base 2 to binary. If we want to go in the other direction, there are, again, a lot of different ways to go in the other direction, right? Converting, let's pick an example, 167 to base 2. It really relies on you knowing these different values of the bits. And so I know that 128 is 2 to the 7th. Right, and 256 is 2 to the 8th. So 128th is the largest number that fits into 167. So that means I have a 1 followed by 6 somethings. because this is 2 to the 7th. 0, 1, 2, 4, 0, 1, 2, 3, 4. Oh, I am missing one, right? 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5th, 2 to the 6, 2 to the 7th. Okay, so then I subtract 167 minus 128 is equal to 39. Okay, my next digit is half of 128, which would be 64. 64 is bigger than 39, so that means that's a 0. And then I go from so no 64. Half of 32 is, or half of 64 is 32. So we go 39 minus 32 is equal to 7. So now we put a 1 in that position. No 16, because that's the next one. After we go 128, 64, 32, 16. So there's no 16. There's also no 8. So that's also a 0. And once you get down to this number, you say 7. Oh, I know what 7 is, right? 7 is 1, 1, 1. And I know that, so I can just fill those in. But that's the method that I would use, pretty systematic, to convert to base 2. Now let's talk about 2's complement for a second. Okay, so this page is just base 2. I should make a note of that. Why don't I make a note of that? This is unsigned base 2 for binary. Okay, what that means is that when you're in unsigned, that means your numbers cannot be negative. They're only positive. So 2's complement came around because it allows us to represent negative numbers in base 2. And the cool thing about base of 2's complement is the way it's designed is that you can add positive and negative numbers at will, and you'll always get the right answer. And this is really important in hardware because you don't need a separate piece of the hardware to do subtraction. You do it, you simply add, and you're good to go. And so you know how to do this in base 12, right? If I want to subtract, I can instead add and have a negative number. And so let me talk a little bit about how that works here. So let's go through the example. 16 is easy, right? There's our binary value for 16. Let's talk about negative 12. So the way you do a negative 12 in 2's complement is you start by representing the positive version of that number. 1 plus 2 plus 4 plus 8. So this is 8 plus 4, and that's where I get my 12. Then you flip every bit. You can see that I basically swap every single one to 0 and vice versa. And then I add 1 to it. This procedure right here is how you create a 2's complement representation of like the negative version of that number. I can go backwards in the other direction. In other words, if I have a negative number like this and I want to know what this represents, I flip all the bits and I add 1. And you'll come back with this number. And so if you don't believe me, I suggest you pause the video and try it. This is really important, right? And this, again, allows me to add plus 12 and minus 12 and get 0, right? That's why it works. So now that we have these two values, we have 16 and we have negative 12, we can add them. And we also learned in CS160 how to add two numbers in binary is the same as adding in base 10. We just go right to left. And if the two numbers add up to 2 or 3, then you have to bring a carry across. Just like when you get to a sum that adds up to more than 10, you got to bring a carry across. So 0 plus 0 is 0, 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 0 is 1, 1 plus 1 is 0 with a carry. So we have a carry up here. 1 plus 0 plus 1 is 0 with a carry. 1 plus 0 plus 1 is 0 with a carry. 1 plus 0 plus 1 is 0 with a carry. And so what we get here is we get, okay, and which is 4. And that gives us our answer. Now, there was a carry that went over the edge here, right? And we learned in CS160 that a carry that goes over the edge could be overflow. There's no overflow. If you're adding a valid positive number and a valid negative number, the answer will always fit. You think about that for a second, right? If you have a calculator, and you will never overflow. if your positive value fits and your negative value fits. And so the overflow detection that needs to happen inside either the operating system or inside the hardware knows, it basically checks these first digits and makes sure that if they're different, we ignore overflow. So there's your 2's complement in a nutshell. One more thing that I want to talk quickly about 2's complement here, which occurs to me, which is called sign extension. Positive number 4 is represented like that, right? It also could be represented like that. It also could be represented like that. In other words, the number of leading zeros, it doesn't matter, right? Just like on your car odometer or on a meter and your gas meter at your house, they'll have those early zeros on there. So a negative number works the same. So if we say negative number minus 12, we know that that is 1110100. And so again, you can sign extend as many as you want, which by the way also means removing any excess ones. So all 3 of these are negative 12. In 2's complement, that leftmost bit or that most significant bit will always tell you whether the number is negative or positive. And so when I say that I need an 8-bit representation, you have to do your work and then add, if necessary, leading zeros or ones to fill up this space. And so in small negative numbers, you'll see lots of ones, and that could sometimes throw you for a loop. All right, Lab 1's got a bunch of practice on this. Show your work. Feel free to use the internet to check your answers. Lots of apps are out there to help you do that. But if you want credit, I need you to show your work. All right, let's talk a little bit about the power of 2. And so this is the type of question that by the end of this class, and I told my students in CS160, some of you will remember I said this, I want you to be fluent in answering questions like this, right? This is like the key concepts in computer science. If I have a 12-bit field, how many memory locations can be represented by that 12-bit field? The answer is 2 to the 12th, right? And 2 to the 12th is 4,096. Okay, so the fact that I can rattle off those answers tells you that I've had a lot of practice with this. But let's talk about how can you be more fluid than this. This is a basic rule in algebra around exponents. And if I say x to the power of a plus b, that's equal x to the power of a times x to the power of b. So let's go through an example here. So where's my text field? There we go. So 2 to the power of 10 is equal 2 to the power of 4 plus 4 plus 2, right? Because I can make that 3. I can have a plus b plus c if I want to. Which is equal to 2 to the power of 4 times 2 to the power of 4 times 2 to the power of 2, which is equal to 16 times 16 times 4. And you either know this or use your calculator. 16 times 16 is 256. 256 times 4 is 1,024. Works the same in subtraction as well, right? You can do your subtraction as well and do your divisions as well. But this will help you if you see, if I say 2 to the 14th, you could start with 2 to the 10th, and you know that's 1,000. And then you can double and double and double and double, right? So again, getting practice on this will help you, all right? And then, of course, you need to be able to do this in the other direction. And so let's say that you're developing, and your customer says that, hey, my customer database will never have more than 16,000 names. And so instead of declaring this massive memory that's really slow and takes up a lot of space, and you create something that can run on a smaller computer or that takes up very, very little space, the question is, how many bits do I need to get a unique index to each of those 16,000 names? And so our answer here is 2 to the what is equal to or greater than 16,000. Okay, well, if I know that 2 to the 10 is 1,000, then let's count the number of times I double that. 1,000 to 2,000, 2,000 to 4,000, 4,000 to 8,000, 8,000 to 16,000. Okay, so that would be 4 more doubles. So that would get us 2 to the 14th. Now, I didn't notice that I didn't do the exact math here, right? I took that 1,000 and I rounded it down. 2 to the 14th is actually going to be bigger than 16,000. In fact, let me do that in my calculator over here. $16,384. So, which I knew that. I didn't have to do that, but I had a brain check there. So this would be the way that you would solve this in the other direction. Now, realistically today on a Windows system or a Mac system, you would declare this thing as an int. And an int is 32 bits. And so you'd have more than 16,000 names. But we might be talking about different examples where I say a picture, has this much space and it's got 3 billion. How many bits do I need, right? 3 billion versus 4 billion versus 5 billion. All right. Here's my favorite illustration of the power of 2. And this is a story that I remember reading about a long time ago. And honestly, I don't remember if it was told to me by a professor or I read about it or what have you, but it's one that I've always really enjoyed. And it takes us hundreds of years back to the invention of chess. And so this is a chessboard. For those of you that aren't familiar with chess or checkers, it's a 64-bit. It's got 8 rows and 8 columns, and it alternates between 2 colors, usually black and white. And so the inventor of chess was the advisor to this grand king somewhere. And he had just given the king such great advice and averted a war or resulted in a capture of something. It was something really, really good. And the king asked, what would you like? I'd like to give you, your heart's desire for a reward. And the advisor said, here's what I would like. I would like you to put 1 grain of wheat on the first space of a chessboard. And then I'd like you to put 2 on the next and 4 on the next. And in other words, double it each time you go across the chessboard. And once that's done, I would like that grain. The king started laughing. Oh, this is like, boy, the great deal for me. He's only going to get, a bag of grains of corn here. So let's kind of start to go through that, right? I don't think I color coded my text very well. We'll see. Nope. So we're going to have to kind of deal with that. So as I double my numbers, I'm going to see what my challenge is going to be here. An exercise in editing on the fly. And you can see that I know these numbers, right? I just know these numbers. But I'm going to start to abbreviate because and don't worry, I'm not going to do the whole dang chessboard. We'll be here all night. You can see where we're going here. We're at 128,000 here. 256,000 here. We'll just do a couple more. I have 12,000. It's so much easier if I was drawing on a whiteboard, right? All right, I think that's a good place to stop. There we go. And there was a certain point here in the way the story goes, a certain point here where the king realized that he had been had, and you know the story, you know, then gets into these diversions if you read different versions of whether the advisor was beheaded or banished or what have you here. But if you go through this, right, the end result here is this is a geometric sum of 2 to the n from n equal 1 to n equals 64. And I didn't think to go find my my Greek letter to show the sum here. But some of you might know that this is also equal to 2 to the n plus 1 minus 1. So in other words, let's go through that real quick. 1 plus 2 plus 4 plus 8, that's equal to 15, which is one less than the next number, right? 1 plus 2 plus 4 plus 8 plus 16 plus 32 is equal to 63, which is, again, one less than the next number. So if we got this next number, the 65th number, and we just subtracted 1, that would be our answer. And so this is the answer here. 18 with lots and lots of digits here, right? So there's your millions. There's your millions. There's your billions. There's your trillions. So it's 18 million trillion. And the other piece of stat that I thought was interesting is that Wikipedia says that this is 1,600 times the global production of wheat. So there was no way the king couldn't even come close to, you know, making this available for the advisor here. The point that I'm trying to make with this story, for those of you that have stuck with me here, is that if I have a bit field, and let's say I have 32-bit field, if I add one more bit, I double a very, very, very large number, right? In the case of 32 bits, that's 4 billion, right? So I add another number and I go from 4 billion to 8 billion. And so that gives me a massive amount of increased capacity. And you see that here, this upper half of the board, that's our 32, right? That gets us to our 2 billion. And 2 billion is basically, you know, all of that. I mean, that's the number of digits, right? So it shows you that we have a long way to go here. This just shows you that if you're not careful, you can create spaces that are way too big. And if you try to like create an array and you decide to loop in a big number, you are going to run out of memory. You're going to cause your computer to slog down. It's very important that you be aware of that. So these are the kind of some key fundamentals I wanted to show. This may or may not help you on the first lab. Remember, this class is more about programming, but I will sprinkle in this kind of stuff because it's really important that we continue to kind of refresh on it. With that, please post questions, comments in the discussion once you see this, and look forward to seeing your work this week. See you soon.